The next category I want to talk about for the self-supervised learning is using information contained in the video, right? So the video can provide rich information, right? This temporal continuity and motion consistency, and action order, right? So video naturally provide a supervision signal that is time, right? So that's the inherent supervision information contained in the video. We don't have to generate any label, right? So time is an inherent supervision signal we can leverage to train the network. So in this particular approach, they first do this unsupervised tracking in videos. So basically, they can using some unsupervised approach, right? Maybe doing, in the first, you can generate a bounding box for this object, right? Then you can using some of the unsupervised approach, right? Maybe basically based on motion information, right? To track this object towards the end of the video, okay? So you can generate like a track of these bounding boxes across time, across different frames, okay? And their idea is that, let's look at these two videos example, right? So let's say this is the first frame and this is the last frame. Maybe this is the 10th frame, okay? This is the last frame. Because we are doing tracking, right? So the tracked object may most likely will contain the same object, okay? So in the future, if we input these, two, bounding box or patches into the network, in the feature embedding space, they should be very close to each other, right? But what if we select another patch or bounding box from a different video, okay? And this is a different video, which is contain, I think it's a dog, right? And if we do this, and the feature embedding in the feature embedding space, they should be much worse, right? Because they are from the different video, okay? And if you do in the same video, we can do this similarly. And the first video, the first frame of the tracked frame or the random select patch of the same video should be much larger, right? Because we are doing object tracking, right? If we do this in the same video, and they should contain the same object, dog. But if you just random select a patch from the same video, maybe you don't have this similar object, right? If you don't using the tracked object or bounding box, the random select patch may contain a different object. So in the feature embedding space, these two should be far away, right? So the distance should be larger, okay? So they're using this kind of idea to rank, right? So the tracked one, the distance should be smaller. The untracked one should be larger, right? So they are ranking this distance as the objective function, okay? So that's their kind of like a supervision signal in their pretext task using the video. Another one is we can using the temporal order of a video, right? So as I mentioned, right, the time is inherent supervision signal. We want to leverage that. So basically we can, select 3 frame, which in the original temporal order, and we can maybe shuffle them into the incorrect order, and we can ask the network to predict, right, if this is the correct order or this is the incorrect, right? So this can be like a binary classification, right, positive or negative, okay? So they do this and using these 3 frames as an input tuple, right, and input to this CNN network. And the output will be, if this is a positive tuple, which means these 3 frames are in the original time order. If it's a negative, then this is going to be incorrect time order, which is, like a randomly shuffle. Okay. So that's another strategy we can using this time order to learn meaningful representation from video. And this is their performance. They compare this kind of tuple verification approach, right? This is a self-supervised learning approach to learn the representation and do this action recognition on this action recognition data set. So UCF 101 HMDB is the action recognition data set. as compared to like a randomly initialized network, right? So they are able to perform better, okay? Since we talk about this jigsaw puzzle, right, in the image domain, so we can also make a 3D version, right, in terms of video, right? So basically we can, for each of the frame, we can divide these one frame into patches, and we can also do this in the temporal dimension, right? So basically now instead of 2D patch, you have this kind of 3D cube, right? Now you do this kind of Rubik cube, right? Instead of like a 2D puzzle. So again, this basically you can predict what's the right permutation or what's the right arrangement for these different small cubes to form the original entire video. So that's some of the information or some of the supervision signal we can leverage from the video. And we've also talked about this cross modality, right? So in some applications, we can collect data that contain maybe multi models, right? So we have some of the cameras, they can generate RGB images, but is also able to capture depth information, right? So I don't know if you guys played like a Microsoft Connect. So it's being a long time ago, they just connect this product, but that camera is able to produce RGB and the depth information at the same time, okay? And also, videos, you have the appearance and also have audio information. So they have this one-to-one correspondence. So take audio and visual correspondence as example, right? So we can take a video, one stream has the visual appearance. We go through this vision network. Another stream has this audio information. We go through this audio network. And then we predict, right? If this is if it's corresponding to each other or it's not, right? Corresponding to each other means these are taken from the same video footage, right? If not, maybe this appearance, these frames taken from one video, but the audio may be taken from another different video. So we can using this to perform this kind of binary classification and trying to learn meaningful representations for these networks. Okay, so this kind of using this cross-modality correspondence to learn this representation. Okay, so since we've talked a lot about these different strategies you can use for self-supervised learning, and we especially mentioned, right, for medical domain, right? So the label data is scarce and it's quite a time consuming to label the data. So self-supervised learning is going to be a very good solution, right, to pre-train the model and maybe fine-tune a small set of the label set so that the performance can be improved. So I want to just make one example, from this paper. So this is published in ICCV 2021. So they're using this self-supervised model to advance this medical image classification. So the idea is very simple. So what they do is they first leverage this natural image, okay? Because in the natural image domain, we have a lot of data we can collect, right? Not just ImageNet, but we can collect a lot of data from internet. So we can using natural image to do this self-supervised learning, right? Maybe you can do contrast learning, right? SIMCLR, to train a very good representation. Then the second step is when we go to this medical domain, right? We can still using the unlabeled medical images, right? Maybe some of the data set like the chest X-rays still have abundant medical data, but they are unlabeled. We can further pre-train on this medical data, right? Because the learned representation on natural image has some data distribution shift as compared to the medical data, right? Because there are some domain gap. So by the second step, we further pre-train the model on the unlabeled medical images, the domain gap can be reduced. And the third step is we supervise fine-tuning on the labeled medical images, right? So in this case, we have a labeled data, but compared to this unlabeled data, the number of samples can be very small, okay? But this is the final goal, right? Because we want to do classification well on these particular data, so we can fine tune it on this small set of label data. In their paper, so here on the left side, so they basically do very similar, right? This is basically the same CR structure, right? So input image, you generate 2 copies, right? Because coming from the same data, you want to maximize the agreement. So this is the usual same CR or contrast learning process. In their paper, they also mentioned this one multiple instance contrast learning approach is because some of the data set, for one particular example, they may contain multiple image. So this dermatology image, right? So corresponding to this one particular patient or maybe one particular disease, they have like a left and the right hand image, right? So in this case, you don't have to do data augmentation to generate 2 copies. The data set already provide like this multi-view image. So you can directly using like 2 of them as the positive pair, right? And go through this kind of contrast learning approach and to maximize agreement. So that's basically, they are referring to this multiple instance contrast learning. So just leveraging some of the characteristics of the medical image data, okay? And we can look at the result here, right? So they are using this ResNet architecture. And if they using the ImageNet pre-train and fine-tune on the data set, they have this accuracy. But if you look at, right, if they're using this contrast learning approach, and they do this ImageNet pre-training, and you get a higher accuracy as compared to a supervised one, right? But if you look at their method, like if you take extra step, right, first pre-train on the ImageNet, then fine-tune it on the dermatology data, the second pre-training stage, right, they mentioned here, self pre-training on the unlabeled medical data image, right, to reduce the domain gap, you are able to further improve the performance, right, from 66 to 69, okay? And if they further using their multiple instant learning, right, they are able to, again, gain a little bit improvement because the augmented data may not be perfect in this case, but you have the actual data to form the positive pair. The performance can be further improved a little, but not significant. Okay, so this is the case of using self-supervised learning in medical image computing. So there's a lot of resource you can look into, especially you can go to this survey paper, right? So they summarize different self-supervised learning technique for medical image analysis, but the core technique are coming from the natural image domain. So this contrast learning is just some of the modifications or training strategies may be improved or modified towards the medical image analysis. So if you're interested, you can go to this survey paper to check out some details. But overall, the core technique presented in this lecture should cover some of the popular method for self-supervised learning. Hopefully, maybe in your own applications, you can consider self-supervised learning as a pre-training task so that you don't have to rely on a large-scale, labeled image data set, but you can still able to achieve very good performance if you only have a small set of labeled data. Okay.